Hello everyone. Welcome to Georgia Water Resource Conference 2021. My today's presentation is about a study on the assessment of corrosivity of atmospheric environment on steel structures. We are from the Georgia Southern University Statesboro campus. I'm Ehsanul Kabir and my respected supervisor, Dr. Salman Hadzazi from the Department of Civil Engineering and Construction. Corrosion is a very familiar term to all of us. Generally, it means rust on a metal surface, as we can see on the figure. But in a broader sense, corrosion means natural degradation. It has been documented as the fundamental cause for tragic failures of various systems and infrastructure. Atmospheric corrosion, on the other hand, is an electrochemical process. It depends on the presence of electrolyte. The very usual electrolyte is water, which is also a universal solvent. Thin film electrolyte tends to form on metallic surfaces when a certain critical humidity level is reached, say approximately 60%. We all know that this humidity level is not constant. It depends on numerous factors such as the properties of the corroding materials, the hygroscopic nature of the corrosion products, and most importantly, when there are pollutants in the atmosphere. However, if we look back, we can see how little time was spent on atmospheric corrosion studies compared to the other topics related to steel structure design. And surprisingly, the atmospheric exposures encountered at these sites are completely different to that of the test sites used for evaluating corrosion. That is why the objective of our present study is to conduct a short overview on atmospheric corrosion in steel structures. We will differentiate between two standard corrosivity determination techniques called the plate penetration test and the coulometer. Finally, I'd like to draw a conclusion and say which one is the better for practice. When we talk about corrosion resistance, structural steels are categorized in three major types. The carbon steel with a maximum copper content of 0.02%, copper steel with 0.2% copper content at least, and the weathering steel which has the sufficient corrosion resistance when compared to the other two. Weathering steels are low alloy steels. This means they have 0.2% carbon, allowing them with various amounts of phosphorus, silicon, nickel, chromium, and copper. The American Society for Testing Materials categorized these three types of structural steels into standard designations for their specific use. For example, A7 steels are used for bridges and buildings. A36 are carbon structural steels, whereas A242 and A588 steels are referred as HSLA, that is, high-strength, low-alloy structural steels. To get into more detail, we conducted detailed review. Albrecht and Hall Jr. collected thickness loss data from 14 atmospheric exposure studies that have been performed since the mid-1930s. These test sites were situated at 6 different states, such as California, North Carolina, New Jersey, Ohio, Pennsylvania, and Michigan. On the other hand, Granata et al. Placed coulometer and the penetration test sites at 3 states called the Michigan, Pennsylvania, and New Jersey. But in their case, they took existing steel bridges as their test specimens. Now we will see how corrosivity can be determined using the standard testing methods. For the plate penetration test, plate specimens of specific dimensions are placed at an inclination while keeping them elevated from the ground surface, as we can see in figure 1. As we know that copper content between 0.21 to 0.3% have little effect on thickness loss data of structural metals, that is why variation of copper steel ratio is used to determine the relative severity of the exposure test sites for plate penetration tests. On the contrary, coulometers are placed on test racks and clamped with the lower flanges of the steel girders of existing bridges. This coulometer consists of a copper cup with a layer of glass beads on the bottom and a steel screen resting on those glass beads, as we can see in the video. One important thing about coulometer technology is that atmospheric corrosion is completely different to the wet corrosion environment. There is no long-term, continuous, ion-conducting liquid electrolyte phase that could be monitored using the conventional electrode system. That is why a thin film electrode is used in the coulometer method. Now, after specific exposure periods, plate specimens are removed from test racks in the plate penetration test. Rust on steel plates is removed by putting them into 75 degrees Celsius, 10% sulfuric acid solution. Mass loss due to corrosion is converted into average penetration per surface using the given equation. Here, C is the average thickness loss in millimeter, K is the conversion constant, W is the total mass loss in grams, A is the total exposed surface area in centimeter square, D is the density in gram per centimeter cube. Albrecht and Hall Jr. found that the corrosion rate for the first 10 years do not remain constant for both carbon and the weathering steels. But there was no recommendation for such thing in the ISO corrosivity band. That is why they modified the ISO medium corrosivity band C3 and proposed a new equation to consider the steady state. In this equation, C is the average thickness loss, R average and R linear are the average corrosion rate and steady state corrosion rate respectively in millimeter per year, and T is the total amount of wear that has been taken into consideration. Whereas in the coulometer, corrosion products are formed on steel screen or the monitor, and ECL is used to get the total output in millicoulombs. The relation between corrosion and the coulometer is described by the Faraday's law. Here, Q is the total amount of charge in coulombs, I is the total current flowing through the cell in ampere, T is the time of current flow in seconds, W is the total weight of material in gram, F is the Faraday constant, and equivalent weight is the weight of the material in gram equivalents. One problem of coulometer technology is that the ECL needs to be changed after certain time periods. For that, the ECL needs to be removed and placed on a device that will reset it and can be used for future uses. The performance ranking for the structural steels remained same for both the test experiments, as we can see on the table. Now, to see the corrosivity against atmospheric environment, additional studies are carried out. For atmospheric environment, we must consider three types of exposures called rural, industrial, and marine, as we can see in their decreasing order of corrosion resistance performance in the table. One thing that came into light after these additional studies is that atmospheric environment can produce more thickness loss despite the type or weight of the structural steels. To recapitulate, I would like to say that although plate penetration tests gave good results for determining corrosion of structural metals, but they are not appropriate for steel structures. Practically, components of steel bridges will face random orientation to skyward and groundward surfaces. In addition to that, a bridge side in close contact with polluted surface deposit will exhibit more thickness loss than the prediction. The coulometer technology can account for all these situations. Moreover, it can give corrosion value at any given time period because there is no specific exposure time required for like the plate penetration. But we must keep in mind that it is the atmospheric environment which boosts corrosivity rather than the structural steel type. So this study has opened up avenues for us to conduct more detailed researches on long-term atmospheric corrosion modeling using the numerical methods. We are very much looking forward to it. That's all from today's presentation. We are happy to answer your questions. Thank you everyone for your patient listening.